As Michael mentioned before, I'm here to go into more detail on one of the projects that Proofcraft is working on, that is verifying a multicore version of seL4. I'll be talking about both the work that we have already done in this area and also our roadmap for the future that we believe is both practical and provides benefits to the community as soon as possible. So, seL4 is the world's most highly assured operating system kernel, but there's an important caveat. Its highest level of assurance only holds on single-core systems. In a little bit more detail, by this I mean that seL4 is only verified to behave correctly when the code that makes up the kernel runs sequentially, without any interference from the other components of the system. Having said that, what do we as developers building systems on top of seL4 actually want? Well, I think that it is safe to say that we all want better performance, and that one way we could achieve this is by making use of the multiple cores that most modern platforms provide. And then, considering that we're all here and using seL4, I think it is also safe to say that we do actually want high assurance software. These two desires lead to us needing to deal with both concurrency and formal verification. And I'm pretty confident that everyone here will agree with me that both of these are each hard to get right, and that it then might not come as a great surprise that doing both at once and verifying concurrent software is even harder. Having said all that, our goal at Proofcraft is to allow seL4 developers to make use of multiple cores as soon as possible, while we gradually provide stronger and stronger assurance as we work through the difficult verification problems. With this goal in mind, the rest of my talk can be divided into roughly 2 sections. I'll first go into a bit more detail about why verifying a multicore version of seL4 is hard, along with exploring the proof of concept framework that has been developed for doing this. In the second half, I'll go into more detail on the specific seL4 configuration that we are targeting, in particular both why we have chosen to work towards this one first, and what our specific plans are for increasing its assurance. So, why is this hard for us? Now, I know that quite a few of you are saying to yourselves, is it hard? Don't we know how to verify concurrent software? And you'd be right. There are a wide variety of techniques for doing this, but they generally work best for small and self-contained programs, or are best suited at a more algorithmic level of software. And in our case, seL4 is none of these things. Even though it is a microkernel, it is still pretty large for something being formally verified. It is definitely not modular, and it is full of low-level detailed code, being a microkernel. Additionally, the existing verification framework that seL4 currently uses is already pretty complex. As we've just heard in Michael's talk, it is large, it's made up of multiple distinct layers, and it needs to support a whole variety of different configurations and features. Putting this all together, this means that for us, none of the existing literature can be immediately applied, and that we need to adapt the existing sequential proofs in a way that allows us to reuse as much of them as possible. Having said that, what do these existing proofs look like? For the purposes of this talk, similarly to Michael, I am going to focus on the part of the proof concerning functional correctness. There are, of course, additional properties that we've proven about seL4, but the functional correctness is the first and, in some sense, the most important component of its assurance story. At the highest level of abstraction, we model an seL4-based system like the one shown here as an automaton, which consists of 3 possible transitions. So there is one on the left representing steps performed by the user components in the system. The transition at the top is for calling a user calling into the kernel for whatever reason, and then the one at the bottom represents the kernel call itself, which is modeled as a large atomic transition, and that includes returning to the running user. For functional correctness, we focus on this bottom transition, the kernel one. In reality, this is, of course, a sequence of the smaller steps made up of all 10,000 or so instructions that make up the kernel code. But as we are at this stage in a unicore setting, we are able to assume that no other transitions are possible while the kernel is running. And so it can be modeled in this as an atomic step. As a bit of a spoiler, I'll be coming back to this assumption in not very long. The proof of functional correctness is then that this atomic transition representing the C code behaves exactly as the equivalent atomic transition of the specification says it should, yeah. Okay, so that's roughly functional correctness for this in a sequential setting. What would it look like in a multi-core setting? Well, to start with, our automaton would now consist of multiple copies, one for each core, and at every step, the next transition could be within any of them. Now that we have this, and now that we are considering a multi-core setting, there is the possibility of code interactions during each of these transitions. You know, while something is running on one core, something else is running on a different one, they might be interacting. For our purposes, there are broadly 3 types of such interactions that we need to consider. First is when we have user code running on multiple cores at the same time. The correct behavior here depends on the overall design of the system being developed, and as such is out of scope for us while we are focusing on the kernel itself. Any approach used to reason about such a system would, however, need to be able to handle this concurrency, and I imagine that we will be hearing more about this in some of the other talks throughout this week, and possibly in the one immediately after. So that's the first type of concurrency. The next we consider is when user code is running at the same time as when a copy of the kernel is executing. For this, we will need to prove that the user code is not able to affect the correct execution of the kernel, which fortunately for seL4 we expect to not be too difficult due to the very limited overlap of memory between user and kernel code. There's not actually many ways for them to directly interact with each other. Which brings me to the main source of complications, reasoning about kernel code running simultaneously on multiple cores. Here, whatever kernel implementation we use has to ensure that these interactions do not compromise the correct behavior of the kernel, and we would then need to prove that this is done correctly. So there are broadly 2 approaches that the existing implementations of multi-core seL4 use. The symmetric multiprocessing configuration uses locks to control these interactions, while the static multi-kernel, we are able to reason that the interactions themselves are safe due to code on each core operating disjointly, operating on disjoint resources and memory regions. Okay, so those are the 3 types of concurrency, and having gone through them, I can now come back to that assumption that a kernel core can be modeled as an atomic transition. This isn't true now. So to be able to handle these types of concurrency, we require that our automaton and verification framework is able to actually model the kernel as a sequence of smaller transitions as it is. It's no longer atomic, it is smaller steps. Okay, so with all of that in mind, what does this mean for us when we're verifying it? So to provide the expected assurance for a multi-core version of seL4, we are going to need a new model and a new verification framework that is able to handle all of these potential forms of concurrency. So that we can complete this verification so that it's feasible within a reasonable amount of time, whatever framework we develop needs to reuse the existing sequential proofs wherever possible, which again, fortunately for us, we expect to be the case for the majority of the existing seL4 code base. And as I've been alluding to, as part of the team at Trustworthy Systems in the past and ongoing now at Proofcraft, we have developed a proof of concept framework that we believe will meet all of these requirements. So the next section of my talk, I'm going to give you an idea of what this proof of concept framework looks like. But first, we return to the existing sequential framework. As Michael showed us earlier, it consists of 3 layers, formalization of the C code at the bottom, and then 2 more abstract specifications above. So a quick warning here, this part does get a little bit more technical, but my aim here is just to give you all an idea of the different components that make up the framework, and so you don't try to remember all the specific terms that I'm about to throw at you. Or you don't need to, at least. Okay, so having said that, the sequential framework is built up from several different concepts, including a monadic language for the specifications, shown at the top. We use Hoare logic for proving invariance about these specifications. We have a notion of refinement for proving the connection between the layers. There's a language called simple for the C formalization at the bottom, and there is a parser that takes the actual C code and produces that simple formalization. If we now compare this to the proof of concept concurrency verification framework that we have developed, we can see that it follows a very similar structure. There is one new layer in the middle that we'll come back to shortly, and otherwise all of the component concepts that I just mentioned are replaced with new, quite similar ones that are concurrency aware. So here again, I'm not going to go into much detail on all of these different concepts. I just want to, for this talk, go do a small dive into the monadic language that we use, as it allows me to show the main way in which we plan to maximize reuse of the existing proofs of seL4. So again, to start with, what does the sequential framework use, and how do we modify it? So the sequential framework uses what we call the non-deterministic state monad, which is a state transformer that takes an input state and produces an output state and a result for the return value. As the name suggests, it is non-deterministic, so it actually produces a set of such outputs to represent all of the potential execution paths. If you are not already familiar with concepts like this, then you can think of this monad as a way to formally express how a piece of code might change the state of a system when run. So in practice, using this monad looks and can be used like a relatively standard functional programming language, as can be seen in this example, taken directly from seL4's abstract specification. So this function, as the name suggests, does a fault transfer between 2 threads. And again, you don't need to understand the details of what this function is doing, but for my purposes, we can divide it into 3 sections. So it starts off by reading some local kernel state and constructing the fault message that it is going to send. Then it calls set message registers, which as part of its execution might write to the receiver's IPC buffer elsewhere in memory. And then the final section of the function writes to more local kernel state. So with that very quick introduction to the monad and this example, what would it look like if it had to deal with concurrency? Well, as I mentioned earlier, to be able to reason about the potential effects of concurrency, we can no longer treat this function here atomically and instead need to consider all of the smaller transitions that it really is. We can show that like this, where each of these points mark somewhere that the state of the system might change due to something running on a different core. However, if we again consider the structure of this function, set message registers is the only step that might actually interact with code running on other cores. This is the only function that writes to non-local kernel state. Which means that while in reality we do have all of these interleaving points, we can instead view the function something like this, where the start and end sections can again be treated as atomic, and we can reuse the existing sequential proofs that we already have for them. So this concept is something that we call limited interference, and it is, as I've already mentioned, an important part of our strategy for reusing our existing proofs. The idea is that our abstract specifications, shown on the left, will have as few interference points as possible so that we have large blocks of atomic code between them. The base C formalization will still match reality and allow for full concurrency, as we can see on the right here. And then there will be a new refinement step in between showing that this limited interference is safe. Assuming that we have correctly identified all of the required interference points, we expect that the proof showing that this is safe will be relatively straightforward. Just quickly, for those that are particularly interested, I don't have time to go into the details of the new specification language that we have built for our concurrency-aware framework, but it is called the interference trace monad, and by construction it is very similar to the existing sequential monad that we were just looking at. So the main difference is that it now additionally produces a trace that allows us to model the potential interleavings that occur while the function is executing, and that there is an interference command that we can use to explicitly mark where that concurrency might happen. So yeah, this would be what that function looks like with this new monad. It's exactly the same, we just mark the specific interference point. Okay, so coming back to our proof of concept framework, that new layer I sort of skipped over earlier is exactly where we introduce the limited interference into our proofs, and where we'll need to show that it is safe to do. The specifications and proofs above this layer are where we then plan to treat as much of the kernel as an atomic block as possible, which, as I keep on mentioning, will allow us to reuse the existing sequential proofs. All right, so that's a quick introduction to our proof of concept framework of how we plan to verify a multicore version of seL4. Apologies if this did go into a little bit too much detail, but hopefully you at least got the idea that we have a proof of concept framework and that it will allow us to reuse much of the existing proofs. However, even with that, this is still a large change that touches all of the components that make up the existing framework, and that will require a lot of work from us. So the obvious question is, how are we actually going to apply this approach? Well, this is where I come to the second part of my talk, Proofcraft's roadmap towards a verified static multi-kernel configuration of seL4. Before we get to that, though, I should answer why aren't we targeting the symmetric multiprocessing configuration? So this is the most flexible configuration for making use of multiple cores that currently exist for seL4, with one copy of the kernel managing all of the cores in the system and using fine-grained locking to maintain consistency. However, unfortunately for us, reasoning about the correctness of these locks would require us to immediately switch to the full concurrent framework, and we would not be able to provide any assurance to anyone building on top of this until we complete the whole proof. So instead, we are targeting the static multikernel, which is not quite as flexible, but is just as useful for the majority of real-world use cases that everyone we have talked to actually has. And importantly, for this configuration, we can straight away start to build an assurance story for it. So I'm not a systems programmer, so I'm not going to go into much detail on how the static multikernel is actually implemented and used, but the central idea is that each core in the system is managed by an entirely separate copy of the kernel, each with their own resources and data structures. And nicely for us, this immediately eliminates all potential kernel-to-kernel interactions, which is one of those types of concurrency that I was talking about earlier. From the user perspective, there is limited cross-core communication possible, and this is true even with the user-facing seL4 API remaining nearly identical, which means that the actual changes to the kernel are relatively limited. So just quickly, the static partition of memory that the static multikernel uses simplifies verification even further by additionally eliminating the other type of concurrency I mentioned, user-kernel interactions. And again, even with all of these simplifications, this configuration already provides more utility than all the other kernels that I'm aware of that claim multicore verification. So finally, as promised, our roadmap for verifying the static multi-kernel configuration in a way that provides incrementally increased assurance. To start with, I would actually argue that this configuration has so much code in common with the sequential configuration of seL4 that it already has some base level of assurance. So assuming that the separation of kernel resources is correct, then all of the common code can be treated as sequential, and the proofs for that code can still be trusted. So then the first step of our roadmap is to extend those sequential proofs to include the few small code changes that the multi-kernel configuration does make. In good news, this is something that we have already done. Although, of course, we might find that further changes are still needed and might need to come back and iterate on this step. So the next stage of the roadmap is that because of the simple design of the multi-kernel, at this stage we expect that we will be able to predict most of the proof obligations that the full concurrency framework will eventually demand from us. And so, so the central obligation, for instance, is going to be that the separation of resources between copies of the kernel is maintained. Identifying them at this early stage doesn't provide any increased assurance on its own, but will directly lead into the next phase, where we formally state and prove these obligations. So completing the proofs at this stage does increase our assurance that the implementation behaves correctly, but again, it is still sequential at this stage, and it would leave us open to having missed obligations, or maybe we might have just formalized it incorrectly. So these risks still appear at this stage, right? We don't have full assurance, but will disappear later on once the full framework is used. As a first step towards that full framework, we will need to parameterize the specifications so that the new concurrent automaton that we will be using can be formalized with multiple instances of the kernel. So this is a bit of a technical step, so I'm not going to go into much more detail on what that means, but instead move to the next phase where we make use of this to actually extend the automaton with all the additional transitions across the multiple cores in the system. At this stage, the big kernel transition in the automaton will still be atomic, but we expect this to already make quite a few of the interactions between kernels on different cores visible, and so it will validate quite a few of the obligations that we previously identified and proved. So as part of this, it also might lead to us discovering new proof obligations that we would then iterate on and be able to show hold at this stage. Of course, while all of that is going on, we also need to complete our proof of concept framework. There are, I have to admit, some parts of the framework that are maybe more conceptual than others. And once these parts have been completed, we will want to exercise the framework fully. So beyond the simple examples that it's currently being used on, and use it to model the full seL4 specifications. So finally, having completed all of these previous steps, we will switch the automaton to full concurrency. If we successfully predicted the proof obligations earlier on, and the concurrency framework rules have been properly validated, then this would ideally just be a problem of putting all the parts together. Of course, this would still be a large step with a lot of work required, just because of how large the proofs are, but we expect it to be mostly mechanical, and to have had a lot of the risk taken out of it due to the completion of all the earlier stages. And then at the end of this step, we will have a concurrent seL4 execution model and a full functional correctness proof for the static multi-kernel configuration of seL4. So just to quickly conclude, with that as our roadmap, we believe that the static multi-kernel is the fastest path to providing the community with a verified seL4 that can make use of multiple cores. And we have a plan to get there, with each step of the plan providing increased assurance. And with that, thank you.
So earlier you presented that that your characterization of concurrency is adding in interference points into the model, into the the monadic representation, what sorts of restrictions do you have to place, assumptions, let's say, you have to place on those, on what happens at those interference points, and how do you express those?
That is a good question. In the specification, we keep it generic. The interference points are allowed to do whatever. And then in the proofs, I didn't mention it particularly, but we are planning to use a technique called rely guarantee to be able to add relies on what the code in other cores is allowed to do. So, for instance, if the kernel is running on another core, it is only allowed to modify its local state, which by construction will not touch our local state.
Okay, so currently the interference will havoc everything. Like you could change anything, but you'll then be adding a relies.
Yeah, you restrict it within the proofs.
Okay, do you have a plan for making sure the relies and guarantees lined up?
That is, we will have to do that as part of the framework. Like, once we introduce all the full automaton, it will force us to do that.
Hey, so the big advantage of the multi-kernel is that you've split up the memory, right? The kernel state memory. You're not interfering on that in principle.
The big advantage for verification.
Okay.
Yes.
Right, and so you can sort of think of the kernels as atomic and separate. But they are, of course, still sharing all of the other system state, right? These things are effectively managing the TLBs and the caches and the IMMUs and everything else in there. So as I've learned over the years, there is an enormous amount of interference and concurrency in there. And the architecture folks have some pretty clear ideas about what you can and cannot do in there, right? In particular, there are some restrictions which are probably not actually required, but mean that you're supposed to keep all the TLBs in sync at all times, right? Yep. Which you have no way of enforcing in a multi-kernel. Have you talked to the ARM folks, the ARM architecture folks, or the people working the ARM semantics? Because they have some pretty clear idea, about how fiddly this is all going to get.
Okay, so I haven't. I don't think we have, but Goen may correct me if this is... Okay, we haven't.
We are thinking about those problems. So we're looking into it. I think the main thing you mean is that you have to synchronize assets in the TLBs.
That's the specific one I was mentioning, but there's a lot more.
Yeah, there's a whole bunch of other system states. Some of it, TLBs as such are actually separate per core, but there are some requirements of what in them has to be in sync. There's a bunch that can be separated. There's a bunch that has to be coordinated. We'll have to look into basically what practically needs to be done. Yeah, that's part of that is in the list of list obligations. That's where we want to drill into each of the bits where okay, we have to assume, I don't know, for instance, in the interrupt controllers, we have to assume core 1 sets them up first, and then the others only use them in a specific way, things like that. And those might actually lead to small kernel API changes, and so that's what Corey meant with we might have to iterate on what new APIs are necessary for the multi-kernel. We'll get to that once, as we go through the project, basically.
I'll take one more, but it'll have to be quick.
So you have a bunch of atomic steps, and then you merge them together in your atomic refinement proof. So I assume those initial atomic steps or the small step come from the small step semantics of the simple or the complex, right? So that's like at the C level, right? But programs that are going to be running on the hardware are going to interact at the assembly level. So, how do you know that the small step semantics you use actually matches up with what's actually going to run?
Yeah, that is a good question. Goen has his hand up to answer it, so that makes it easy for me.
Okay, 30 seconds. The short answer is it won't matter, because we're getting rid of the interference on a way bigger level already, right? Where we're saying, oh, it doesn't even matter if you write to memory at the same time, because you're writing to very different memory. If you're writing to memory in 5 transactions or in 1 transaction, it doesn't matter if it's completely separate anyway. So that's the main argument for that. And that would not work for SMP, but it will work for multi-kernel.